Okay, for engineering and social experimentation, it's one of the first of several key ideas in engineering ethics. The next one we'll be getting into are safety and risk. It's the following. As a good example is, to start with, is the Titanic. Okay, so I don't know how many people have seen the movie. I don't know these days if that's still quite a few have seen the movie. Okay, so I'm going to just, so the big boat, brand new, fancy, highest tech boat ever created, leaves, sails from England, I forget what port, and is going to sail to New York City. And as it's sailing across, it sideswipes an iceberg, and it rips the side of the boat. Boat fills with water, and the boat sinks. Okay, and there's some fantastic scenes in that. Actually, 1,522 people died. Over 1,000 were saved, though. They don't say things like that in the movie, but so what happened when this boat started to sink? You remember in the movie, the first mate or the communicator guy or whatever went to the wireless room, and they called nearby boats to help out. Turns out those boats came and picked up people and saved people. Okay, now this was a high-tech boat, and other boats weren't like this, but it helped save a lot of people. Turns out after they discovered how useful wireless could be on a boat via this Titanic incident, the maritime laws changed to make wireless required on boats. Okay. Now, another thing that happened that was probably perhaps just as important. Do you remember in the scenes in the movie where the people would walk along the decks and look out into the ocean? Well, turns out that you also will remember the big fights over the boats, the lifeboats that were dropping over the side, putting people in, etc. Well, they didn't have nearly enough lifeboats for all the people. Okay? That was a basic problem. And the question is, why didn't they? Well, it turns out they wanted those beautiful scenes that you could see or sit and drink your beverages and look out over the ocean. They wanted lots of free space like that. Well, that's where the boats needed to be. Okay? So they did a trade-off between having nice viewing spaces versus having boats, and that's what they came up with. They had nowhere near enough boats. Okay? Laws changed in that respect, too. So, why is this engineering as experimentation? So you do this big engineering project, you put out this fancy technology, it screws up, and then we say, oh, let's redesign it. And then it continues like that. And there's many, many examples of systems like that today where we deploy into the public, we find out after deploying that we screwed up, and then we redesign. And we can look at, there's tons of examples with software. For instance, the latest release, the Apple iPhone 6 and 6 Plus, and the iOS 8.0 that had a bug, went to 8.01, had another bug, went to 8.02. Okay, so they're using the public to test their software, right? They're deploying it, letting people start screaming and say it's bad, then they fix it. Okay, so they're using, and all the major software companies do that. Microsoft, of course, does it all the time. It has done it for years. Okay, so this problem of software engineering is really quite, in terms of software test, piece of software engineering, it's really quite difficult to do the test. So it becomes very expensive to do software testing, so you ask, how much should I do? Okay, especially if the software is quite sophisticated. All right, so Microsoft Word is a pretty sophisticated program. The OS, Apple's OS, iOS, is a pretty sophisticated system, and it is very difficult to test. Of course, they're doing testing to some extent before they release it, but they're not doing the full-scale test with millions of people using it in all different ways that the public provides for them. So the public's providing them a service. It's like we're becoming co-designers for them. And it can be upsetting at times, right? Because you're like, you know, it just ought to work. Your best option, people say, is to simply don't click download until a month after the first release. So everybody that did click download were the guinea pigs. They all encountered problems, and then the company fixes those problems, and you get a good, clean piece of software. A lot of people do that. When you do software tests in a company, historical information is used about how much test to do. And the problem is, however, is every piece of software is new, therefore don't exactly know ever how much to test it. Well, that's really frustrating. So because of that nature of, you're here to drive technology, to create new technology. By creating new technology, you get in a realm where you don't know how to test to make sure it works. Especially technologies that can injure people, such as anti-skid braking systems, which are electronic, for instance. So our projects are often projects that involve technology development and humans and human safety. And that's where our concern will lie. So the design process that you may have already learned about or are going to learn about soon typically goes something like this, where you have concepts. You might have some, these are design concepts, what you ought to do, preliminary designs and tests. You may do more detailed designs and more tests that cost money. You go into production, you may do more tests, and then you release it to the public. The public gets the product, and what do? Well, they don't think of it as doing a test, but from your perspective, they're doing tests on your product, okay? And there becomes a problem of how do you gather the results of their tests. I mean, you just gather gross data. Let's say you're General Motors, you put out a defective ignition switch, okay? And it goes out and somebody, you just collect accident data or data on how many people died, okay? Let's hope not. Let's hope you're trying to collect more data than that so you can look at redesign. They were, well, they got themselves in a mess. I mean, this ignition switch thing is, I hope you read about it on the website. It's fascinating. It's a simple mechanical problem where if you put extra stuff on your keychain, okay, like it makes it a little heavier, it can switch the car off when you drive. And 19 people were killed. And they knew about the problem and should have fixed the problem. But of course, that cost them a lot of money, right? This is when the decisions are made of lives versus technology redesign. So do you you admit you have a problem, which doesn't look good for your company. Then do you do a recall on, 1 million vehicles or something like that? And then you have the cost of the fix. Okay? So it can be very expensive. But of course, it's best to come clean and fix the problem as early as you can fix the problem. So this process, because of this dashed line, where the public's testing the product, and while testing the product, they can get injured. There's this unfortunate situation that engineers are often put in where it's sort of a dangerous situation. You sort of scratch your head and say, when should I release this product? And you just may not be sure, and that's all there is to it. Okay? But you've got to try to be as competent as possible so you're as sure as possible so you don't screw up and hurt people or kill people. So there's some similarities to standard experiments. And there's some differences. In engineering projects, they're really always carried out in partial ignorance. That isn't referring to the engineer. That's referring to what you know about your design. You may have a resistor with a plus or minus 20% value. You don't know what the true resistance is, right? So the same thing holds for materials, whatever. So engineers, the problem is we're asked to make things work without all the available scientific knowledge. We often do things, we put things together, make contraptions, and the science isn't sort of in and settled. There's no class you could take that would teach you more science about it. It's just not known. like for instance, there's something in the chemical process control called the distillation column that's been used for many, many decades. And nobody knows how it actually really works, but it works very well, okay? So we also don't know about safety facts. We learn safety facts from our products because we go test them on 1 million people or more. Then we learn how safe a product is. But then, of course, you're being asked to create a new technology. You don't know how safe that one will be. Okay. We don't know how things affect the environment. There's been a growing emphasis on the environment in the last 10, 20 years, especially the last 10 years in engineering. And the reality is we might have tested things with respect to safety, like for injuries, accidents, deaths, but we often have not tested our products and how they adversely affect the environment. There's much more work that needs to be done that. Affecting health, sometimes the environment, sometimes the social influences. Good design relies on information gathered before and after a product leaves the factory. So it's nice if your organization is put together so that when you get everything engineered, goes to manufacturing sends the product out the door. It's nice if you have engineers also monitoring what happens after it goes out the door, rather than just being put on the next product. And that can be quite a problem, okay? This is especially the case when products are trusted in the true environments, not the fake ones are used in the real environment. I once worked for an engineering company where they made electronic radios, and they would take the radios to make sure that it worked, and the radios were used in critical situations, not just for entertainment, and they would put it in what they call the shaker. Well, basically it was a steel platform in a big oven where we heat it up, cool it down, and shake it, and change the humidity, change the temperature in the chamber. We do all of this stuff to it to see if they could break it, to simulate what we like out running around outside in the woods or whatever. Okay? That, of course, is not a real environment. I mean, the real environment is when you take 1 million radios, you give them to 1 million people, they go out and try them, then you find out what the real environment was like. Okay, so we use public to perform tests, and it's well, in my lifetime, it's become more and more. It was this notion of the software update that we use now from Microsoft and Apple, etc. I mean, that's relatively new. It's only about 10 years old. It used to be that was sort of, in some ways, unacceptable to use, essentially, use the public, the users of the software, to help test your product and update your product. You know how there's a lot of, I don't know how some of the software programs do it, but some of them, when there's an error, let's say something crashes or whatever, it comes up and says, can we send information to XYZ company, blah, 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 and you click yes or no. Okay? So that sort of thing has become much more acceptable, and it's done quite a bit more often. All right, so we obviously need special care to avoid lost customers. What that means is you want a reliable piece of software, for instance, because customers' perceptions of a company change based on the reliability of the software. I think these big companies just threw up their hands and said, we're spending too much money on testing, we're just going to release it, and then only a certain number, let's say 500,000 users use it, they find all these problems, then they put the software update out, and then most people don't experience the problem. I think that's the way they sort of trade this off, okay? So your diligence as an engineer certainly matters, but you have to learn from the past. This is difficult when you're a young engineer, you join a company and you want to know what the safety history is of similar products, the sort of generation 1 and 2, when you're trying to generate generation 3. You want to know about those things. Well, problem is can you always know it? And the answer is no. You got to be as competent as possible, learn as much as you can about the product, think outside the box about what kind of safety things can become a problem. You have to be open to learning. You have to want to learn, and you've got to be not afraid to ask. And sometimes what this means is, yes, you got to go talk to the old engineer because they often, they might be a curmudgeon, but they often know a lot about safety, reliability, history of a product that you can learn from to help you do better. Another problem is that you like to know the competitors' safety statistics. You do know that, for instance, there's a lot of reverse engineering that's done out there, and somehow it's considered normal practice. For instance, in the automotive industry, so one time, years ago, I went to Delphi Chassis Division of General Motors to visit. Walk in, the first thing I think I'm going to see brakes, from General Motors. I walk in, the first thing I see is Toyota brakes on the stand being tested. I'm like, guys, what's going on? And they explained the whole system, how whenever the first person or entity to buy General Motors car when it comes off is Ford and Toyota, and then likewise. And they go in, they rip them to pieces, and try to figure out what they're doing to help. So they're reverse engineering. They're looking at this and saying, "Oh, we can do this too," and they do this in very fine detail. So accident statistics, they don't get full accident statistics. Those are private to company, but they can get something about their designs, okay? And they can look at consumer reports or other reports on safety, and they can figure certain things out. But there's not a full information sharing, at least in this country. The law says that you can have proprietary information about such things. Another problem is there are good communication channels even within your own company, between different departments or cross generations of engineers. Often there is a dangerous generation gap between young and old engineers. Old engineers, I've met some really irritating old engineers. I mean, that could be an issue because they're sort of old and depressed, and they're no fun. It's always this "no, we can't do that" attitude. It's really sort of a whole different philosophy from what you'd like to have as young technologists getting things going. So, but you got to try to work across these sorts of boundaries because they can sometimes really help quite a bit. So some contrasts with standard experiments. Do we have control experiments? The answer is no. We can't control what humans may do with a product. What applications will it be used for? Will they subject it to unforeseen stresses? And then the cornerstone of how this is supposed to work with engineering is you're supposed to create a product and tell them, the customer, everything about the product. Okay? This is the key. So this is the so-called informed consent, such as in medical trials. This is the keystone of the engineer-public interaction. So the question is when you put out, is it okay to put out some technology and inform some people? That's like an experiment then, right? Run my experiment. But the question is what is acceptable? Because there's many types of customers. So for instance, do you have to assume that your customer can read when they may not be able to read? What if they're young? What if they're a child? What if they're quite old and can't see? There's many issues that arise, and knowing about how to release your technology when it comes to safety. Basically, it's wise to try to seek the unexpected and design for that. So, being a responsible experimentalist, we try to be conscientious and protect safety knowledge and respect the right of the consent of the public. We don't have secret pieces of your technology that may be dangerous. Okay. Comprehensive perspective, being aware of the experimental nature of products. You have to forecast in the future and monitor what's happened. Moral autonomy means you got to try to stand by your product and make sure it's working properly. And you have a right to do that as an engineer, especially when you want a product that has safety implications. This is not easy for engineers to do engineers often, create some product that has safety implications. It gets released to the public, and guess what happens? They get reassigned to another job. Okay? So it's very difficult for engineers to monitor the status of what's going on after their products leave, and then, of course, they don't know how to do a redesign on them to improve them so that they're more safe the next time around. And then there's the issue of accountability. Whether you like it or not, the lawyers can come after you if you screw up on this kind of stuff. Okay, so you do have responsibility. Sometimes that responsibility is fragmented in an organization across a group, for instance, or more than one groups, or it's said that it's diffuse across the whole organization. One of the big issues, and we're going to be talking about this more later, is the issue of time pressures. You want to make sure that the product is as safe as possible, it's tested enough, but you have to put it out the door. Okay? Because of time pressures, trying to get to market the fastest to make more money, to beat the competitor to market so that you gain better market share, things like that. So, one of the other problems here is that engineers aren't the sole ones in charge of this. There's managers and marketing people and the public. The problem from your perspective is that if you understand the technology, which you will, you've got sort of a special responsibility to make sure that it is a safe product. Okay, so we're in a unique position as engineers to monitor projects, identify risk, and develop facts for informed consent. So a good engineering professional will certainly take on those responsibilities. Now, I'm going to mention, I got 2 slides here on law and engineering. I'm not going to do law and engineering. That would take several semesters to cover that topic. I think it's very interesting, though. These are sometimes called the rules of responsible experimentation. So laws can produce many benefits. They can produce minimal standards of professional conduct, for instance, with respect to sexual harassment or something like that. They can provide a motive to comply with standards. Well, I don't want to break the law. I'm going to get my butt thrown in jail, so I'm not going to do that. All right? Provide support and defense for people who wish to act ethically. So we're not covering the engineering law here, but there's a lot of you that will learn some of this on the job. Quite a few of you, a number of you will take on jobs that have to do with a manufacturing organization, and you'll learn things like OSHA law, okay, and so forth, these industrial standards. The problem is these laws are extremely detailed. You've got to be careful with that because they can take a long time to learn. There is a notion of minimal compliance with the law. There's minimal compliance. We're going to have case studies on this a little later, where if you just do this, you won't break the law, but it's not enough because it would still correspond to unethical behavior. All right, so it'd be morally unacceptable. And then one of the problems with the law is it's always out of date with respect to our area of engineering. Why? Because we're continually pushing the technology forward. They don't make out laws for every new piece of technology that comes out. And therefore, the law is continually trying to catch up. Okay? And there's a sort of balance between how much law you have, and then the government's influence on that and setting rules, and the moral autonomy of engineers. You sort of don't want to squish the moral autonomy. You don't want to hurt the advancement of good technology that can help people reduce toil, provide more safety, protect the environment, etc. So there sort of has to be a balance between all of these things. So I'm going to do a number of case studies. All of these are from students from this class. Okay? So these are students that have seen engineering as experimentation in action. All right? So, first student. I was involved in designing and testing network communication software. Some tests were still being run when clients requested the software. We were unable to finish the test and gave the product to the customer, knowing the system caused lockups and loss of data. We then used the feedback from these clients to debug the software and repeated the process. Standard, okay? So this thing that you see with Apple and with Microsoft is happening at all levels, okay? It's just that they might not have auto update, right? I mean, they have to come back, and these people would have to redesign their communication software to try to fix things. You have to, as an engineer, realize you may get pretty good grades. The fact is, when you start creating complex systems and technologies, you're not going to always get it right. I mean, that's just a fact. And so even your whole team may not always get it right. Even your testing on what you've done may not always get it right. So you have to continually monitor and test, and then when it goes out, they test too, and you have to try to monitor what they're doing and respond to these customers. Let me ask you a question. In this case, for this student, should you tell the client that you're releasing this software when you're less than confident that it's going to work?
Provide automatic updates, then there's no reason to.
And add an as-is cost of
Well, he didn't bring up the automatic updates, so yes.
But an as-is clause in the middle of the license agreement. Nobody reads that.
Yeah, you can be assured then that no one will read their license agreement.
I read it.
No, but look, I mean, these kind of situations, you're going to find a lot of engineering works on the back of relationships. Relationships that you have with your clients. So if you want to look these people in the eye, shake their hand and say, this is our best effort. Do you want to do that in this situation? Or do you want to say, look, we're not real certain, we think it's all right. Can you watch out for a problem? We'll fix it as soon as we can. I mean, I'd be really careful to be honest with your client, because otherwise you're going to disappoint them. You're going to hurt the reputation of your organization. You're going to hurt your own reputation. So why not just come clean and say what it is? Maybe what you need is this auto software update possibility, and maybe you ought to start working on it, because it does help in a lot of ways. I mean, you can do that. Snap. It's not just them finding the error too. Sometimes you go to the next product. All right, so you release the product, it goes out. You start working on the next version, generation 4, and you realize you made a mistake in generation 3, right? This happens all the time. Then you just click on that software update, boom, it's, no embarrassment whatsoever. It just happens. So, next case, a similar student case. In software engineering, I've encountered problems in that the time required for testing the product and the deadline for testing may conflict. And some parts of the testing may have to be compromised to meet those deadlines. Very similar situation. A big warning. You don't have to be a software engineer to be this. I mean, a lot of ECEs write software, right, for lots of pieces of systems, not just pure software systems, but systems, for instance, like electromechanical systems, like an anti-skid braking system has electromechanical parts, and it's got software algorithm running there to decide how to modulate the brakes, okay, to get you to stop as soon as you can. So this sort of thing comes up all the time. Computer testing. On a recent co-op job, my company had just shipped the latest and greatest computer product. After a few months in the field, it was found to vastly lack the processor power it needed to do what it claimed to do. A fix that followed had to be the shortest turnaround time I'd ever seen. The fix was top quality, but the damage had been done. Full-scale test or even simulation would have predicted this problem before shipping. What this is really about is being responsible within the organization to do these sorts of things, like simulation or some type of a test. What does this person mean by the damage had been done? Well, you can really hurt your reputation of your company in these kinds of situations, right? You don't want to hurt the reputation of your company, right? You want to make money for your company. I mean, remember, that's why you're getting a job, right? You're getting a job to make them money. Well, you're going to make money at the same time. You make them money, you make money, everybody's happy. So you're concerned with the reputation of your company so that they can make good money. Okay? Of course, you're concerned with your own reputation. Why? Because you're going to have a performance review. And your raise can depend on these kinds of things. Meeting specifications. In my co-op position, I was placed in a design team to create an audio system. The project was a classic example of marketing wanting the product so bad that timelines were regarded higher than the quality of the product. The audio system's first prototypes arrived with many problems, some of which could not be resolved until after the product was released. It basically came down to the decision of letting the consumers find all the problems and then hoping that the management would provide the team with more time and funding to fix the problems to try to keep the customers happy. Boy, I can tell you, whatever company you work for, there's sort of an orientation of a company with respect to whether it's sort of business-oriented, marketing-oriented, whether it's engineering-oriented. There are a lot of engineers that are employed by companies that are not engineering-oriented, in the sense that the engineers don't have the authority in the company. They're just like the little worker bees that go and create the technology, and the marketing, business, lawyer types manage everything else. And boss them around, push them around. I've seen this. Push them around, and the engineer essentially has no voice. It's quite a problem. And it can get you into an ethical problem, too. If you're to have moral autonomy, you're to try to do a good job, well, you've got to have the freedom to try to do that. That's very important. Environment. A turbidity meter was used to monitor if contaminants were getting into the water that goes into the river. Think local river, because it was the Olentangy. When those meters failed to alarm us and a white pigment went into the river, my project that focused on redesigning the monitoring station was given support. Interesting, right? So I put out this thing, and the technology, the meters failed, okay? And then they fixed the problem. In the meantime, what happens? You screw up just a little bit of the environment, okay? But at least they fixed things, okay? And didn't ignore what was happening. Next, in wastewater treatment plants, control systems are tested in the field. The control systems are designed according to specifications and ISA IEEE rules, but the testing of how the systems will operate under real-life situations is done after installing them. Two questions arise then. First, can the plant design withstand additional rain, population increases, weather problems, etc.? And second, can the control system adequately analyze these new factors and operate the plant successfully? If anything fails, the great danger is release of raw sewage, sludge, and bacteria onto land and the water supply. This is a very frustrating sort of technology. It's a very nice description the student provided of the challenge. It turns out that these systems can't be tested before they're released. It's a very odd situation with technology. Most technologies can be, tested to some extent. The problem is that simulation technology has not advanced enough to simulate a whole grid of water and sanitation for a city like Columbus that's going to be accurate. And therefore, what they do is they do the best job they can. They release the technology and let it run, and then they say, "Ooh, it messed up," or "Wow, it's doing great." But the key is these engineers that do this are watching each other. Often these are public, so that you can be watching California, you can be watching Nevada, you can be watching Massachusetts, and these systems tend to work pretty well because of that, in spite of not being able to do tests before actual implementation. Next. My problem came with the company involved with design and manufacturing of PC power supplies. Some manufacturing organizations have focused on 100% minimal compliance and had substituted parts to achieve their cost objectives. This resulted in unsafe final consumer products. An industry push for CSA and UL certification of power supply submodules enhanced the minimal level achieved for standard subassemblies. Since the FCC and FTC act as police organizations, it's not usually known that there's a problem until much mayhem occurs. When other companies began selling smoking PCs, the industry began to push to use only modules which would meet UL and CSA standards. The minimalists were forced to up the ante or lose considerable business. This describes very nicely the process, right? So the process is you hit the law, you know, minimal compliance, you put your technology out for your PC power supply, and then problems occur. The PC literally starts on fire. I don't know if any of you had that happen. I have. It's not pleasant, especially if you're sitting on an airplane. It starts on fire on your lap. But when these things start breaking down, then these government organizations step in and say they have to be better. Then that changes the law, and then the problem's fixed. You see the iteration, it takes time, and it's slow to get fixed, unfortunately. Meeting specifications. The heated hoses we manufactured were using a 100 ohm platinum RTD substitute. The hose resellers were rating the range of heat as higher than the RTDs could actually model linearly. We had years with no problems until one customer started running the protocol at the top of the temperature rating. We immediately stopped production, found another RTD that would be suitable. All stock was pulled and rebuilt. The fix took almost a year. Interesting. So what happens is you're creating a product. You've got a set of customers you're regularly trying to satisfy, and they're all operating in some range. Everything's fine, everything's working good. New customer arrives, operates differently at a different temperature range. Your system will fail into that range, and they go back and do a redesign. There's not a lot of detail here. I wonder if they contacted that customer and told them not to use their old product and wait the year for the new product. I'm not sure what this student did. Successful use of customers in testing. Welders built for an alpha run of a production were sent to a select group of customers to be tested in the field. The customers did have informed consent that these machines were in the early stages of testing. Many changes were made based on their feedback. Interesting. So in this situation, you got a welder is an electrical device, right? So electrical engineers are designing this thing, and they're not sure if they got it right, and they're finally like, well, let's just get some trusted group of customers, some subgroup, tell them exactly what your concerns might be, put them out in the field, and have them test them. Maybe you give them a discount in future sales or whatever else. Okay, so bring them in, be a part of the team, be completely honest with them. Why not? Could be a good idea. Next, I want you to, in this case, it's longer. It comes from NSPE, and we're going to try to recognize where engineering and social experimentation is occurring. So engineer A is employed by a software company, is involved in the design of specialized software in connection with the operation of facilities affecting the public health and safety. Does that sound familiar? Okay, so the third time we've talked about this case. Nuclear air quality control, water quality control. As part of the design of a particular software system, engineer conducts extensive testing, and although the tests demonstrate that software is safe to use under existing standards, engineer A is aware of a new draft standards that are about to be released by a standard setting organization. These are standards which the newly designed software may not meet. Testing is extremely costly, and the company's clients are eager to begin to move forward. The software company is eager to satisfy its clients, protect the software company's finances, and protect existing jobs, but at the same time, the management of the software company wants to be sure that the software is safe to use. A series of tests proposed by engineer A will likely result in a decision on whether to move forward with the use of software. Tests are costly and will delay the use of the software by at least 6 months, which will put the company at a competitive disadvantage and cost the company a significant amount of money. Also, delaying the implementation will mean the State Public Service Commission utility rates will rise significantly during this time. The company requests Engineers A's recommendation concerning the need for additional software testing. You remember, this is a difficult case because of all of the trade-offs. Now, question, where is social experimentation in the study? You want to be able to recognize when it exists. So, in the case study, it was via the social experiments that they came up with new standards. The old standards that were in place, okay, they show that there's not enough testing to catch a problem with the software. In the new standards, they were invented to capture the problem via new standards. It's that step. It's the implementation of the software under the first conditions up here, okay, when it doesn't work, and now we find that it doesn't work, and therefore we update the standards. That's the step for social experimentation, okay? Question you might ask is, where will that trend lead us over the years? The problem is it leads us to more and more detailed laws, guidelines. Hopefully it leads us to a more and more safe system. But does it ever end? Maybe not, because there's always new things that you encounter, so you don't know if the process here would ever end. Okay, we're finishing a little early today, aren't we? No, just a little bit, 5 minutes. Okay, so attendance question is, name as many technologies or systems that ECEs are involved in designing, maintaining, or improving, and that involve important safety considerations. Okay, so that's the first piece. Second piece is describe any examples of engineering and social experimentation that you've seen in the engineering workplace. Safety concerns for the next lecture, but do not mention company names. If you're not comfortable having your name associated with it, just write your name on one sheet of paper, write your answer on another sheet of paper. That's fine. All right? But please don't mention company names. I don't want to say company names out loud in class that they're coming up with, especially in bad cases of engineering and social experimentation, where somebody's getting hurt or somebody's health is significantly adversely impacted. Hi, how you doing?
Good. Quick question. So this next Monday, there's this graduate research organization that's all day. They said they would send out an email to the professor. I would have to miss class that day. I'm just wondering how. It's like 4 students that want to speak. It like gives an overview. I can show you the email. Oh, we have one. Okay.
Send me an email.
Yeah.
Great.
Yeah.
So that I can get it for you.
Okay. Thanks.